Right, in this video, we'll talk about section 8.3. This deals with testing a claim about a mean. So here we continue with chapter 8. And in this video, we're going to develop the ability to use sample data to conduct a formal hypothesis test of a claim made about a population mean. Now, we already talked about the basics of a hypothesis test in section 8.1. And in section 8.2 in the last video, we talked about testing a claim about a population proportion. Now we're going to look at a population mean in this video. Okay. All right, so the only thing I'm going to cover is part one. Part two deals with the procedure used when a population standard deviation is known, but that's rare. Okay. So in reality, as I stated, it is rare that we test a claim, very rare that we test a claim about an unknown value of a population mean, but we somehow know the value of the population standard deviation, okay? Now, the realistic situation is that we test a claim about a population mean and the value of the population standard deviation is not known. When sigma is not known, we use what they call a t-test. When sigma is not known, we use a t-test that incorporates the student t-distribution. Okay, so the requirements, the test statistic, the p-value, and the critical values are going to be summarized as follows. So here, the notation where n is the sample size, x bar is the sample mean, mu sub x bar, or just mu, will just be the population mean, and this value is taken from the claim and is used in the statement of the null hypothesis. Okay. Now, there are two requirements. One of them is that the sample is a simple random sample, meaning that samples of the same size have an equal chance of being selected. And number two, either both of these conditions are satisfied. The population is normally distributed, or your sample size n is greater than 30. Okay. Now, these are similar requirements for those testing, but not testing, writing a confidence interval, constructing a confidence interval estimate for a population mean. Okay, so these requirements are pretty much the same. Now, the test statistic that we will use for testing a claim about a mean will be this. It is a t-test, so it's going to be t is equal to x bar minus mu divided by s over the square root of n. Your x bar, again, is your sample mean. Mu is the population mean, and that's found from the null hypothesis. S is the sample standard deviation, and n is the sample size. All right, so to find the p-value, we're going to use technology, or we can use a student t-distribution, which is table A-3 with degrees of freedom given by df equaling to n minus 1. So table A-3 is this. Those are your critical values here. All right. Now, more than likely in this video, we're going to be using technology because the table itself won't give you the exact p-value. So the best way to find that p-value is to use technology. Now, if you were doing the critical value approach, then table A-3 would work, because in that table, you have to find your degrees of freedom on the left side. And if you remember, when we did section 7.2, there are two rows, the area in one tail and the area in two tails. You use the row for area in one tail if you have a left tail or a right tail test. Area in two tails is only used when you have a two-tail test. And then you look for the corresponding critical value for that. Now, of course, if you use table A-3 to find the critical value for t, but the table does not include the number of degrees of freedom, you could use a conservative. You could be conservative by using the next lower number of degrees of freedom found in the table, or you can use the closest number of degrees of freedom in the table or interpolate. Okay. Now the properties of the student t-distribution pretty much is just a reminder of that when we talked about constructing a confidence interval for a population mean. The student t-distribution is different for different sample sizes. Okay. So for each sample size, there's a different student t-distribution. Also, the student t-distribution has the same general bell shape as the normal distribution. Its wider shape reflects the greater variability that is expected when S, the sample standard deviation, is used to estimate the population standard deviation sigma. And then the student t-distribution has a mean of t equals 0. And then your standard deviation of the student t-distribution varies with the sample size and is greater than 1. And as the sample size n gets larger, then your student t-distribution gets closer to the standard normal distribution. Okay. And these are just some strategies for finding the p-values using the t-distribution. Best advice is to use software. And in this video, I'm going to be using a TI-84 plus calculator. We can also use Statistic, Minitab, Excel Stat, StatCrunch. They all provide p-values for the t-test. Okay. And then use table A-3 as a last resort. Okay. Now, p-values can be easily found using computer software or a TI-83 or 84 plus calculator. This difficulty of finding p-values can be avoided by using the critical value method of testing hypotheses instead of the p-value method. That is, if you use table A-3 that I just showed you. Okay. All right, so here I provided the keystrokes for using what we call the TCDF command on the TI-84 calculator. And it's also on the TI-83 as well. Number one, you want to press second and then bars for the DISTR menu, which is your distribution menu. So here's the 84 that I have here. Second and bars gives you the distribution menu. And then you'll scroll down to find, use your down arrow key to find the command that says TCDF and then press enter. All right, now, for those of you who are using the earlier versions of the TI-84 or the TI-83, your screen is going to look like this. It's going to have TCDF with a left parentheses. And then you're going to enter the lower limit, the upper limit, and your degrees of freedom. They'll be separated by commas. And if you need to know where the comma key is, it's right above number 7. That's this button right here. It's above number 7. So the format will look like this: TCDF and then lower limit, upper limit, and then your degrees of freedom. And then finally, you'll press enter. Now, for the newer versions of the TI-84 calculator, like the one I just showed you here, when you do second bars and then go down to TCDF and then press enter, your screen is going to look like this. TCDF would be in the middle, then you have lower, upper degrees of freedom, and then paste. You'll first enter the lower limit, and then press enter, and then type in your upper limit, press enter, then type in the degrees of freedom, and then press enter. And then you'll press enter again to get your p-value, okay? Now, after finding the test statistic and the number of degrees of freedom, the p-value can be found using the TI-83 or the 84 plus calculator, okay? Now, I've already gone over these two steps right here. Now, here's how we find the p-value, by using the number of degrees of freedom and the test statistic. If you have a left tail test, then your p-value is going to be the result of this. After TCDF, the lower limit would be Now I use a negative with 6 nines. Now you can use more than 6 nines. That way you can get a more precise p-value, okay? Because a left tail test goes on to the left indefinitely, so I would use a negative with 6 nines or more, and then test statistic, then degrees of freedom. Now, of course, on the 83 and the earlier 84s, you have to use commas separated. A right tail test. If you have a right tail test, then your p-value is going to look like this. After you type in select TCPF, the lower limit will be your test statistic. The upper limit will be 6 nines or more. And then degrees of freedom. And keep in mind, degrees of freedom is n-1. Now, if you have a two-tailed test, then the p-value is going to be the smaller of the following two results. And that's going to be this, twice the value that's obtained from this. Now, here's a hint. If your test statistic is less than 0 or if it's negative, then I would use this format right here. The negative with 6 nines or more, test statistic, then degrees of freedom. Or it would be twice the value obtained from this. Now, if your test statistic is positive or greater than 0, then I would suggest using this format. Type in the test statistic first and then 6 nines or more, and then degrees of freedom. Okay, now, again, here's that hypothesis testing procedure that I gave you back in section 8.1. We'll be using that again to help us test a claim about a population mean. We've used this before to help us test a claim about a population proportion. Okay. All right, now let's look at some examples. And that's this. 12 different video games showing violence were observed. The duration times of violence in seconds were recorded. When using the sample for a t-test of the claim that the population mean is greater than 94 seconds, what does DF denote and what is its value? Okay, so what do we know about DF? Well, that's the notation for degrees of freedom. We did talk about that. Okay, and we did talk about that back in section 7.2 in a previous video. So DF denotes degrees of freedom. Now, what is its value? Well, 12 different video games, that's your sample size, n is equal to 12. So that means your degrees of freedom is n-1. And n is 12, so if I do 12 minus 1, that would be 11. So here I have 11 degrees of freedom. And that's all that they asked for in this example. Okay, now example 2. The display provided from technology available below results from using data for a smartphone carrier's data speeds at airports to test a claim that they are from a population having a mean less than 6.00 megabytes per second. Conduct the hypothesis test using these results. Use a 0.05 significance level. Identify the null and alternative hypothesis, test statistic p-value, and state the final conclusion that addresses the original claim. Well, in this case, if I do that 8-step procedure that I showed you, we can answer these questions here. Okay, so now, here's that 8-step procedure again. The first step is to state the original claim in symbolic form. And in this case here, the claim is that they are from a population having a mean less than 6.00 megabytes per second. So that's your mu. Mean is going to be the population mean, mu. Less than is the symbol, 6.00. That's your original claim. Now, step number 2 is the opposite of the original claim. We know it's going to have the mu, the opposite of less than. If it's not less than, then that means it has to be greater than or equal to. That's the opposite, 6.00. Less than, the opposite is greater than or equal to, or greater than, the opposite would be less than or equal to, or equal to would be not equal to. Those are your opposites. Step number 3 is to identify the null and alternative hypothesis. Now keep in mind, the null always has the equal sign in it. So even though it says greater than or equal to, we just write that as mu is equal to 6.00. And that mu is less than 6.00, that will have to be the alternative hypothesis, because the alternative hypothesis has either less than, greater than, or not equal to. So the mu is less than 6,000. And I'm writing the word claim because that is the original claim, that mu is less than 6.00. All right, now step number 4 is to state the level of significance. And in this case, we're using a 0.05 significance level. So alpha is equal to 0.05. And now step number 5 is to identify, well, calculate the test statistic. However, it's already calculated for you if you look at that display. And here it is. T is negative 3.696725. But in this case, we want this to 2 decimal places. So this will be T equaling to negative 3.70. T equals negative 3.70. That would be your test statistic. Now, step number 6 is to calculate the p-value. But here's the p-value right here. Now, to 3 decimal places, that would be 0.000. I'm going to write the word out, p-value equals to that. With these calculator displays, they usually use lowercase p as your p-value. But I'm going to write out the word p-value to avoid confusion with proportion. All right, now step number 7 is to decide whether to reject the null or fail to reject the null. Well, I'm going to have to compare the p-value with our level of significance, okay? So here, if the p-value is less than or equal to alpha, you want to reject the null hypothesis. Now here my p-value is 0.000. The alpha level is 0.05. If you compare those two, 0.000 is less than 0.05. So that does satisfy the decision rule. So that means I can reject the null hypothesis. And then step number 8 will be to write the final conclusion that addresses the original claim using simple, non-technical terms. Okay. Now, there was a table that I gave you probably in section 8.2 and 8.1. Now, the claim, let's go back to this. The claim was the alternative hypothesis, and we rejected the null hypothesis. So the claim is your alternative hypothesis, H1. We rejected the null hypothesis. So that means that there is sufficient evidence to support the claim. So when we write our concluding statement, it's going to be this: there is sufficient evidence to support the claim that the sample is from a population with a mean less than 6.00 megabytes per second. All right. So that's how we use that 8-step procedure to test the claim. All right. Now, example 2. A data set includes data from student evaluation of courses. The summary statistics are this: N is the sample size, that's 87. X bar, the sample mean, is 3.41. The standard deviation, S, is 0.67. Use a 0.01 significance level to test the claim that the population of student course evaluations has a mean equal to 3.50. Assume that a simple random sample has been selected. Identify the null and alternative hypothesis, test statistic, p-value, and state the final conclusion that addresses the original claim. All right, so now we're gonna go ahead and use that 8-step procedure. So step number 1 is this: your original claim is this. We're testing the claim that a population of student course evaluations has a mean equal to 3.50. So in symbolic notation, that would be mu is equal to 3.50. And then next is writing the opposite of the original claim in symbolic form. The opposite of equal to would be not equal to. So the mu is not equal to 3.50. All right, now we need to find out which one will be the alternative and which one will be the null hypothesis. Well, in this case, your alternative will have to be the not equal to. So your alternative hypothesis is mu is not equal to 3.50. That means your original claim, mu, is equal to 3.50. This time, your null hypothesis is the claim. We're either going to have sufficient evidence to reject the claim or not sufficient evidence to reject the claim. Step number 4 is stating the level of significance. And we are told to use a 0.01 significance level. So step number 4 is alpha is equal to 0.01. Now, step number 5. is to calculate the test statistic, okay? So here's the summary statistics that's given to us. N is 87, X bar is equal to 3.41, S is equal to 0.67. And I'm also going to include mu, which is your population mean. That's from the null hypothesis. Here, mu is equal to 3.50. Okay. And our test statistic is this: T is equal to X bar minus mu, all divided by S over the square root of N. And then we just substitute in that T formula. X bar is 3.41 minus mu, which is 3.50. That's divided by S, which is 0.67, divided by the square root of N, and N is 87. Now, if we enter this in the calculator, we're going to have to use parentheses in the numerator and in the denominator. Okay, so here's my calculator. I'm going to enter this in. Let me clear this junk out. The numerator will be left parentheses 3.41 minus 3.50, close parentheses, divided by, and then the denominator will be left parentheses 0.67 divided by, for the square root second and x squared, and then 87. Let's use our right parentheses, get out of it, and then close the parentheses, and then hit enter. Now I'm going to round that t value off to 2 decimal places. So this will be negative 1.25, or round off to whatever number of decimal places that the homework asks for. If they say 3 places, then you round it off to 3 places. But in this case, we're going to round it 2 decimal places. So it'll be negative 1.25. That will be the t test statistic. Now, here's how we're going to use the calculator to come up with the p-value, which is going to be step number 6. I'm going to draw the normal curve here. Okay. Negative 1.25, as you can see, is to the left of 0. And if you look at your alternative hypothesis in step number 3, you'll see it's not equal to. That means I have a 2-tailed test. And let's go ahead and find out what our degrees of freedom is. That's n minus 1. N is the sample size. That's 87. So if I do 87 minus 1, I will get 86. So I'm going to have 86 degrees of freedom. And negative 1.25 is to the left of 0. So, and I did tell you this, if it's negative, I would shade to the left. If it was positive, then I would shade to the right in the 2-tailed test. So I'm shading this area right here. And it also tells me that since I have a 2-tailed test, the p-value will be 2 times the area beyond that test statistic. So when I calculate the p-value, that's going to be 2 times whatever I get as the decimal value when I use the TCDF command, which is what I'm going to use. And notice it's shaded indefinitely to the left, so I'm going to have to use a negative with 6 nines, and it could be more than that. And then my test statistic will be negative 1.25 My degrees of freedom, 86. So I know I'm going to have to do 2 times. Here's the calculator. Now, to get the TCDF command, I have to press second and bars. Press second, and then the bars. That would give me this menu. Now, if you look under menu item number 6, or wherever TCDF is, that's the one you want. So I'm going to go down to TCDF and then press enter. That's the screen. Okay. Now my lower limit is going to be, and I'll enter negative with 6 nines in it. Now, if you notice at the top, it has a -1 and then e to the 99. You could use that, or I just go and type in negative with 6 nines, and I can do 9 if I want to. And then my upper limit is at negative 1.25. The negative key is at the very bottom of your calculator, and then 1.25. And then hit enter. Degrees of freedom is 86. That's what DF stands for. Degrees of freedom, 86. Hit arrow to go down the page and then hit enter again. And then enter. You'll get this. And that's going to be 0.107. But of course, it's a 2-tailed test, so I need to do twice that. So I have to take that answer and multiply it by 2. And this will give me 0.215 approximately. And I'm rounding that p-value off to 3 decimal places, or whatever decimal places that the homework asks for you to do. So here, the p-value is 0.215. Reason why I multiply by 2, because it is a 2-tailed test that I'm dealing with. So 0.215 is the p-value. All right, now step number 7. Step number 7 is our decision rule to determine whether we need to reject the null or fail to reject the null. And our decision rule is this: if your p-value is less than or equal to alpha, reject the null. Hypothesis. Now my p-value is 0.215. The alpha level from step number 4 is 0.01. Now, if you compare the 0.215 with 0.01, you'll see that 0.215 is greater than 0.01. So this violates the decision rule. So that means I need to fail to reject the null hypothesis. Fail to reject the null hypothesis. And then step number 8 is right now a final conclusion, or the final conclusion using simple non-technical terms. We failed to reject the null hypothesis, and the claim was the null hypothesis this time. Here, the claim was the null hypothesis. We failed to reject the null hypothesis, so that means that there is not sufficient evidence to reject the claim. So that means there is not sufficient evidence to, let's say, warrant rejection of the claim that the population of student course evaluations has a mean equal to 3.50. Okay. Now, let me tell you, if I had you in a face-to-face class and on a paper test, you would have to write all this out. Okay. Okay, now example number 4 is this. In a test of effectiveness of garlic for lowering cholesterol, 49 subjects were treated with raw garlic. Cholesterol levels were measured before and after the treatment. The changes before minus after in their LDL cholesterol levels in milligrams per deciliter have a mean of 0.3 and a standard deviation of 16.1. Use a 0.10 significance level to test the claim that with garlic treatment, the mean change in LDL cholesterol is greater than 0. What do the results suggest about the effectiveness of the garlic treatment? Assume that a simple random sample has been selected. Identify the null and alternative hypothesis, test statistic p-value, and state the final conclusion that addresses the original claim. Okay. So let's start off with step number 1, the original claim. And the original claim states that, let's see, we're testing the claim that with garlic treatment, the mean change in LDL cholesterol is greater than 0. So mu, we're dealing with the mean, so mu is greater than 0. And now step number 2 is the opposite of the original claim. If it's not greater than, then it must be less than or equal to. So the mu is less than or equal to 0. That's the opposite of the original claim. Now, step number 3 is identifying the null and alternative hypothesis. Well, one of them is going to be the alternative hypothesis because the alternative has either greater than, less than, or not equal to. This one has greater than. That has to be your alternative hypothesis. So your mu is greater than 0. And that's also the claim mentioned in the problem. So your null hypothesis always has an equal sign in it. So the mu is equal to 0. And now step number 4, the level of significance. It says use a 0.01 some level of significance. All right, step number 5, calculating the test statistic. Now let's identify what we have here. 49 subjects were treated with raw garlic, so N is 49. The sample mean for those 49 is 0.3, that's X bar. The standard deviation there, S is 16.1. And of course, I'm going to add that mu is equal to 0. That comes from the null hypothesis. All right. So now, calculate the test statistic. So T is equal to x bar minus mu divided by s over the square root of n. Here, x bar was 0.03. I mean 0.3 minus mu, which is 0, all divided by s, that's 16.1, divided by the square root of n, and n is 49. So if you were to enter this in the calculator, we're going to need parentheses in the numerator and parentheses in the denominator. So here, left parentheses 0.3 minus 0, close parentheses, divided by left parentheses 16.1 divided by, and then second x squared for the square root, 49. Right arrow to get out from underneath the radical, and then close your parentheses, then hit enter. To 2 decimal place your t-value, critical t-value, well, your test statistic as a t-value will be 0.13. Your t-test statistic is 0.13. Okay. Now step number 6. And step number 6 is calculating the p-value, because that's what they asked for. Let's see, 0.13 is to the right of 0. And we have this. In the alternative hypothesis, it is strictly greater than. So that tells me, if you recall, your alternative hypothesis tells you what type of test you're going to have. Since it says greater than in the alternative, that means my test is a right tail test. So that means all of the alpha level will be in the right tail. So that means my p-value is going to be this shaded area right here. So I have a right tail test. Okay. Now, to find the p-value, we're testing a claim about population mean. We're using the p-value approach. We still use that TCDF. But this time, my lower limit is that test statistic of 0.13. The upper limit, since this goes indefinitely, I'm going to use a bunch of 9s, like 6 9s. I could use more than that. And then your degrees of freedom. All right, let's calculate the degrees of freedom up to this side here. That's n minus 1. N is 49. So 49 minus 1 is 48. So I have 48 degrees of freedom. Okay. So now, I do second vars for the distribution menu, go down to TCDF, hit enter. My lower limit is that test statistic of 0.13. Then hit enter. The upper limit would be 6 9s. I'm going to use probably 9 9s or more. Degrees of freedom is 48. Highlight paste and then hit enter. And then hit enter again. If I was to round that off to 3 decimal places, that would be 0.449. Okay, so 0.449 would be the p-value, okay? Notice I did not do 2 times that because it is a right tail test. It's not a two-tail test, it's a right tail test. You only multiply by 2 for your p-value when you're dealing with a two-tail test. Okay, so that's step number 6. Step number 7. Is to decide whether to reject the null or fail to reject the null. And our decision rule is always this: when you're comparing the p-value with your level of significance, if your p-value is less than alpha, reject the null hypothesis. And your p-value in this case is 0.449. You're going to compare that with your level of significance of 0.10. That comes from step number 4. And as you can see, 0.449 is greater than 0.10. So here we fail to reject the null hypothesis. So here I fail to reject the null hypothesis. And then in step number 8 is writing the final conclusion using simple non-technical terms. So in this case here, if I fail to reject the null hypothesis, now my claim was the alternative hypothesis. The claim was the alternative hypothesis, and I failed to reject it. So that means that there is not sufficient evidence to support the claim. So my statement for that would be there is not sufficient evidence to support the claim that the mean change in LDL cholesterol is greater than 0. And the other part of the question asks, what do the results suggest about the effectiveness of garlic treatment? Okay. Well, there's not much to say about that, is that we can't make a conclusion. Now go ahead and write this out. We cannot conclude that the mean population of changes and that's in regards to LDL cholesterol, is greater than 0. Okay. All right, let's look at example 5. All right, a simple random sample of 10 pages from a dictionary is obtained. The number of words defined on those pages are found, with the results being this: n is equal to 10, that's your sample size. X bar, the sample mean, is 65.8 words, and the standard deviation, S, is 15.7 words. Given that this dictionary has 1,425 pages with defined words, the claim that there are more than 70,000 defined words words is equivalent to the claim that the mean number of words per page is greater than 49.1 words. Use a 0.10 significance level to test the claim that the mean number of words per page is greater than 49.1 words. What does the result suggest about the claim that there are more than 70,000 defined words? Identify the null hypothesis and alternative hypothesis, test statistic, p-value, and state the final conclusion that addresses the original claim, and assume that the population is normally distributed. Okay, so we can do a test statistic. Well, we can test this claim. Starting with step number 1, write the original claim in symbolic form. And we know we're going to have mu here because we're still testing a claim about a mean. And it does say, equivalent to the claim that the mean number of words per page is greater than 49.1 words. Greater than is this symbol, and then 49.1. And then step number 2 is the opposite of the original claim. Well, if it's not greater than, then the opposite of that will have to be less than or equal to 49.1. And then step number 3, we write our null and alternative hypothesis. Now we have to think which one will be the alternative hypothesis. And it will have to be mu is greater than 49.1 because the alternative has either greater than, less than, or not equal to. So here, mu is greater than 49.1. And that's the original claim. The null always has the equal to in it. So the mu is equal to 49.1. That's our null and alternative hypotheses. Now, step number 4 is to identify our level of significance. In this case, we're using a 0.10 level of significance. Now, step number 5 is calculating the test statistic. All right, let's identify what we have here. The results are given here. N is 10, sample size, sample mean, X bar, 65.8, and S, the sample standard deviation, 15.7. And mu is equal to 49.1. So now we have that information, we can calculate the test statistic, which is in this case, T is equal to X bar minus mu divided by S over the square root of N. And then we just substitute into this formula. X bar is 65.8 minus mu, which is 49.1, divided by S, which is 15.7, over the square root of N. N is 10. So in this case, I'm going to use parentheses in the numerator and the denominator. And we're ready to find out what our test statistic is going to be. So here, left parentheses, 65.8 minus 49.1, close parentheses, divided by, and then left parentheses, 15.7 divided by, and then second x squared for the square root, and then 10. N is 10. Close parentheses, hit enter. Let's see, the 2 decimal place, that would be 3.3 3.36. So my t-test statistic is 3.36. Now, step number 6 is finding the p-value. Step number 6 is finding the p-value. So now, let me draw the normal curve. .36 is somewhere off to the right of 0. Now let's look at our alternative hypothesis. This says greater than. So that tells me my test is going to be a right-tailed test. Okay. Again, the alternative hypothesis tells you what type of test you have. I have greater than, that means a right-tailed test. So that means the p-value will be in the right tail. Okay. And I need to know what my degrees of freedom is going to be. That's always n minus 1. Your n is 10. So 10 minus 1 will be 9. So I'm going to have 9 degrees of freedom. So now my p-value is this. I'm going to use the TCDF command. Now, first, the lower limit is your test statistic of 3.36, comma. This goes indefinitely out to the right, so I'm going to use 9s. Now I'm only putting 6 9s, but you can use more. And then your degrees of freedom, which is 9. So in the calculator, I'm going to press second and vars, and then go to TCDF, center. The lower limit is now 3.36. Type that in, press enter. I've already got I got a bunch of 9s here, so I'll leave that alone. That'll be 6 9s. You can just type in as many 9s as you need to. Degrees of freedom is 9. Go to paste, hit enter, and then hit enter again. To 3 decimal places, my p-value is going to be 0.004. So here the p-value is 0.004. And now step number 7 is the decision rule to decide whether to reject the null or fail to reject the null. I'm comparing the p-value with my level of significance. So if the p-value is less than or equal to alpha, you want to reject the null hypothesis. And here the p-value is 0.004. My level of significance is 0.10 from step number 4. Now, if I compare those two, 0.004 is less than 0.01. And that does satisfy the decision rule. So that means I'm going to reject the null hypothesis. Here I'm rejecting the null hypothesis. And then in step number 8 is writing the final conclusion using simple non-technical terms. Now, I reject the null, and the claim was the alternative hypothesis. So let me go back to this table right here. The claim was the alternative. I rejected the null, so that means that there is sufficient evidence to support the claim. Okay, so here's my final conclusion, that there is sufficient evidence to support the claim that the mean number of words per page is greater than 49.1 words. Okay. All right, and finally, example 6. A data set about speed dating includes like ratings of male dates made by the female dates. The summary statistics are as follows. You can see N, that's your sample size is 196. The sample mean there, X bar is equal to 781, and the sample standard deviation S is equal to 2.25. Use a 0.05 significance level to test the claim that the population mean of such ratings is less than 8.00. Assume that a simple random sample has been selected, identify the null and alternative hypotheses, test statistic p-value, and state the final conclusion that addresses the original claim. Okay. So basically, we'll start with step number 1, is writing the original claim in symbolic form. And we're dealing with mu, so that means that mu is such ratings is less than. So I have to use the less than symbol and then 8.00. And then step number 2 is the opposite of the original claim. Well, if it's not less than, then mu will have to be greater than or equal to 8.00. These have to be opposites. And now step number 3, the null and the alternative hypothesis. Well, one of these has to be the alternative hypothesis. It has either less than, greater than, or not equal to. So here the original claim would be your alternative hypothesis. Mu is less than 8.00. And I'm writing the word claim because that is the original claim. The null always has the equal to sign in it. So it'd be mu is equal to 8.00. Now step number 4. Stating the level of significance, this time is 0.05. Level of significance. So alpha is equal to 0.05. Step number 4. Now step number 5 is calculating the test statistic. Well, we already have our summary statistics here. Your N is the sample size, that's 196. X bar, which is the sample mean of 7.81. And S, which is your sample standard deviation, that's 2.25. And I'm going to include the mu. That's, excuse me, that's 8.00. So now we can calculate the test statistic, which is T is equal to x bar minus mu, all divided by s over the square root of n. Here, x bar is 7.81 minus mu is 8.00 divided by s, which is 2.25, divided by n. I mean, the square root of n, 196. So in this case, put parentheses in the numerator and the denominator when you're using your calculator. So now left parentheses 7.81 minus 8.00, close parentheses, divided by left parentheses 2.25, divided by, and then second x squared for the square root enter 196, close your parentheses, hit enter. To 2 decimal places, your t-test statistic will be negative 1.18. So negative 1.18 would be your test statistic for t. All right. So now step number 6 is finding the p-value. Using the normal curve, negative 1.18 is to the left. Let's say that's about right there. All right. Look at your alternative hypothesis here. It does say less than. So that tells me that I'm going to have a left tail test. Okay. That means the p-value will be the area that's in the left tail. That's a shaded area. Now, I need my degrees of freedom here. That's n minus 1, and n is 196. Subtract 1 from 196, you get 195. Okay. So I have 195 degrees of freedom. So now I'm going to use my calculator to find the p-value, and I'm going to use the TCDF command. All right, going from left to right, this goes off to the left indefinitely, so I'm going to use a negative with at least 6 nines, and then comma. The test statistic, negative 1.18. That's the upper limit. Degrees of freedom, 195. And that negative with 6 nines, by the way, that's the lower limit. Okay, so on the calculator, we're going to do this. Second, bars. Go down to TCDF. TCDF, hit enter. The lower limit will be negative with, I'm going to use 9 nines. Then my upper limit is negative 1.18. And then my degrees of freedom is 195. And I'm going to hit enter to highlight paste, and then hit enter, and then hit enter again. Now notice that's my p-value. To 3 decimal places, it'll be 0.120. That's the p-value, 0.120. Because p-value is the probability of getting a test statistic as extreme as the one that we obtained from the sample data. Step number 7 is the decision rule. So that's if our p-value is less than or equal to alpha, reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. Your p-value in this case is 0.120. And then the alpha level was 0.05 from step number 4. And of course, 0.120 is greater than 0.05. That means we need to fail to reject the null hypothesis. And the final step is to write our conclusion. Using simple non-technical terms here, we failed to reject the null hypothesis, and the alternative hypothesis was the claim. We failed to reject the null hypothesis. That means that there is not sufficient evidence to support the claim. So we start off by saying there is not sufficient evidence to support the claim that the population mean of such ratings, and that's from the student course evaluations, by the way, is less than 8.00. Okay. Okay, so that's how we test a claim about a population mean, okay? And that will conclude this video on testing the claim about a population mean. Good luck with the homework in my math lab, and feel free to email me if you have any questions about the homework or anything that's presented in this video.